Hello, my name is Joe Jung, and I'll be discussing phase transitions and their consequences in logical satisfiability problems. To begin with, let's start with a brief primer on logic expressions. Logic expressions consist of variables which may be true or false, and operators. The most basic operators are the two binary operators, OR and the unary operator NOT. The first is the inclusive OR, which returns true if either of its two operands is true. The second is AND, which is true only when both of its operands are true. Both the OR and the AND operators are commutative in the usual way. The unary operator NOT negates the value of the expression to which it is attached. True becomes false, and vice versa. Operators can be ordered and strung together to form more complicated expressions. For example, A ORed with B, the quantity, ANDed with C. This is a statement written in conjunctive normal form, which essentially means it's a statement of ANDs of ORs. The basic problem when we're given a statement in conjunctive normal form is usually something called the satisfiability, or SAT for short. Essentially, can we set the variables in the expression so that the total output of the expression is true? That is, what do we assign to A, B, and C so that we get true, or satisfy the expression in the end? One thing to note is that this expression is actually made up of two distinct clauses. The two clauses are separated by the conjunction, or the AND. Each clause itself is a disjunction. This is the basic premise of conjunctive normal form. If we can satisfy both of the clauses, then the overall expression will also be satisfied. This is a specific satisfiability problem called 2-SAT, which is up to two literals in each clause. A different form of this problem might be 3-SAT, where we're allowed up to 3 literals in each clause. For example, this statement here. The generalization is what we'll call k-SAT, where there are up to k literals in each clause. In particular, we're interested when there are exactly k literals, or for 3-SAT, when there are exactly 3 literals in each clause. So how hard is it to solve a k-SAT problem? We'd like to know this for future algorithms work. Fortunately, 2-SAT is very easy. 2-SAT is in a category of problems known as P. In other words, it can be solved in polynomial time given the different number of variables or clauses. Unfortunately, 3-SAT, or any k-SAT where k is greater than or equal to 3, is hard. 3-SAT is in a category of problems known as NP, which means non-deterministic polynomial time. Basically, it's going to take a very long time to solve any 3-SAT problem that's composed of many clauses and many literals. We'll be examining the behavior of solving 3-SAT problems. So how do we solve a 3-SAT problem? Well, basically, we guess. The Davis-Putnam algorithm for solving a satisfiability problem is to set a variable to true, reduce any of the clauses containing the variable, and then run the algorithm on the remainder. If it fails, then set the variable to false instead and try again. So if we take this statement as an example, we'll first start by setting A to true. Well, in the first clause, we know that if A is true, we actually don't care about the rest of the clause. The entire clause is just satisfied. So we move on to the next clause. We know that A is true already, so the first term, the first literal where A is negated, can't be true. So we know that we're relying on the rest of the clause for this to be satisfied. In this case, we'll need either not C or D to be true. Eventually we'll continue on, and we might come across a solution, for example, A being true and C being false. The rest of the literals, we don't actually care what they are. Now that we know how to solve these problems, let's look at some of the behaviors of these systems. First, we'll look at the fractions of satisfiable expressions. Not all expressions are satisfiable. Just how many of these expressions are going to be satisfiable? Well, it turns out that this is going to be a function of n, m, and k, where there are n variables, m clauses, and k literals per clause. What are the odds that, given these parameters, we could pick out a random expression in a certain ksat class and have it be satisfied? Here I've generated 1,000 random 2-set expressions and plotted the fraction that were satisfiable as a function of clauses per variable. The most important one to note here is in green. This is 20 variables. One of the important features of the plot is that most of the time either all of the expressions are going to be satisfiable or all of them aren't. It's the region in the middle that's interesting here. For some critical ratio of clauses per variable, we find that we're transitioning from mostly satisfiable to mostly unsatisfiable expressions. Beyond just the number of satisfiable expressions, we also look at the difficulty of these expressions. Remember that in the algorithm, there are going to be dead ends found. Essentially, whenever we find a variable that doesn't work, we have to backtrack and try something else. This is what I'll call a dead end, or a new branch. Here's a normalized plot of the number of dead ends found while running the algorithm. The number of dead ends found can be interpreted to be the difficulty of proving that a statement is either satisfiable or unsatisfiable. Here the important thing to notice is that as you increase the number of variables allowed in your expression, there becomes a sharper peak in the difficulty. It's easier to see the effects when we overlay the plot of difficulty on top of the probability plot. Here it becomes clear that there's a critical value for the ratio of clauses per variable, where not only is the difficulty of the problem solving increased, but also the actual satisfiability of the problems is changed. We can extend this and look at the 3-sat scenario. Here's the same plot of the probability that any given expression in the 3-sat class will be satisfiable. Observe that in the 3-sat case, the plot is much sharper than in the 2-sat case. When one also looks at the difficulty of solving these problems, there's a pretty clear critical ratio. It turns out that this is a phase transition between mostly satisfiable and mostly unsatisfiable, and that for the 3-sat case, this occurs at a ratio of 4.25 for clauses per variable. Many sources claim that this phase transition is independent of the algorithm used. Although there are many improvements that can be made to the Davis-Putnam algorithm, none of them would get rid of this characteristic ratio of clauses per variable. This means that certain kinds of problems, no matter how efficiently they're approached, will always have this kind of difficulty spike when approaching this critical ratio. For comparison, here's a similar plot with the 4-sat scenario. The moral of the story is that, regardless of the efficiency of the algorithm used, some problems are always going to have this difficult to handle phase transition.